Hello everyone. In this video, I'm going to go through a discussion on asymmetric dielectric slab waveguide. We are going to use optical approach to analyze the PV equations. So to begin with, we have shown the field distribution along the y-axis to be constant and even. In this case, partial y notation will be substituted with 0. So to begin with, let's take a look in the cross-sectional view of the asymmetric dielectric slab waveguide. It's basically a sandwich of 3 layers. So we have the middle layer, so-called the core layer. Normally, the refractive index of the core layer is the highest among all these 3 layers. The thickness of the core is assumed to be D, and the bottom layer supporting the core layer is so-called substrate, and we use refractive index N of 2 to describe this layer. And the top layer is called cladding, and the refractive index is N of 3. And throughout our analysis, we are going to base our analysis on a two-dimensional planes. The horizontal axis is the z-axis, and this is the axis where the wave propagates. The axis along which the wave propagates in the core channel. The vertical axis is called the x-axis. So you can see here at the bottom boundary, x is equal to 0. At the upper boundary, x is equal to d. And the V number is defined as this one, k naught d, and then times square root of n1 square minus n2 square. Square root of n1 square minus n2 square is also called numerical apertures. And the cutting layers and the substrate layers may not be the same. In this case, is a situation of asymmetry. So we are going to use the asymmetry factor to account for these asymmetric conditions. So let's begin with the light pathway going from A to B. As the light heading towards point B, refraction occurred, and the light will be bounced back from B to C. And this is the refraction, just like many other, just like a mirror. It obeys the law of refraction, with the angle of incidence equal to the angle of refraction. And this process go on and on. So now let's take a look in the total phase shift. For this round trip, it's a round trip in the sense that if you focus on the vertical direction only, it go up and then come back. Okay? So during the refraction at point B and during the refraction on point C, there will be a phase shift. The phase shift is assumed to be free for the upper boundary and free 2 for the lower boundary. Now let's take a look in the phase shift from A to B. From A to B, the total phase shift to be involved will be K1 times cosine theta 1. This means the phase shift, the wave number, the three-dimensional phase number, and then multiply cosine of theta 1. And this is essentially Kx, because this is the wave number for the vertical direction. And then, at the bottom, through the pathway BC, we end up with the same phase shift. So altogether, we have one phase shift, two phase shift, and during the refraction, we have one phase shift for B and one phase shift for point C. So if we are going to calculate the total phase shift, delta V, it will be equals to this one plus this one, which is 2 times n1 k0 cosine theta 1, plus the phase shift at point C, which is 3, 2, and plus the phase shift at point B, which is 3, 3. So altogether, we have this phase shift. In order for total internal refractions to occur successfully, we need to make sure each round trip is an integer multiple of 2 pi. So this is what we need. Where m here represent the integer multiple, and m can be 0, 1, 2, 3, but m is 0. M being 0 is meaningless. So we might assume m is equal to 1, 2, 3, and then last one forever. Now if you divide the whole equation by 2, so we end up with this equation. And this is the starting point of the characteristic equation, the dispersion characteristic. The dispersion characteristic will be derived based on this equation. Okay? So let's take a look in the second page. We are going to simplify these equations. So to do that, what we need to do is to simplify each of the terms here using what we have learned previously. From the previous chapter, from the previous slide, we know that this is the wave number in the x direction. And similarly, in the horizontal direction, we just need to do this. And this is the wave number in the z direction. And z direction is beta, the same as beta that you can see in other textbooks. I mean the wave number in the direction of propagation, and in this case you may have shown this is the propagation constant. So from the previous chapter, we have learned Pinel equation. We have also found out the phase shift when a photon is hitting the boundary can be calculated in this manner. So for the lower boundary, the expression is like this. For the upper boundary, the expression is like this. So the only difference between these two expressions lies in the refractive index. The upper one, I mean this equation, N2. the lower boundary is M2, the upper boundary is M3. So equation 1 can be rewritten as like this, because this is essentially kx, and if we substitute v2 into this equation, then you will get this one. If you substitute v3 into this equation, you get this one. So this is the starting point. This is the second step, and we are going to further simplify this equation into another very clean one, PV equations. So before doing anything, we need to have some definition specific to TE mode. We need a V number. The V number is defined to be this one. Yeah, this is the same for other dielectric waveguide. And we need the NF, the effective refractive index. It is defined as N1 divided by Kz divided by K0, and it is actually the parameter measuring the refractive index in the presence of the incident angle. Yeah, with the incident angle here, then the effect of refractive index will be lower, and this is the key for this. And one more parameter, B. B is equal to this one, NU square minus N2 square divided by the square of the numerical aperture. And A of TE here represents the asymmetry factor. And this asymmetry factor accounts for the difference between the top layer and the bottom layer. Between the top cutting layer and the bottom substrate layer. So let's verbally define this parameter. We normalize the propagation constant. We normalize the frequency parameter. A of TE, or just A, is a asymmetry factor. In this case, it's the asymmetry factor for TE modes. For TM modes, all these factors have to be modified. And now we'll talk about this later. And these definitions are going to be applicable for TE mode only. So let's start with the left equation. The left mode parameter of the characteristic equation. So if we expand this, then it will be like this. So now, let's take a look here. The expression is very simple. So first of all, cosine theta here can be replaced with square root of 1 minus sine square. And before doing this, we multiply the top and bottom by the numerical apertures. And now replacing cosine theta with this one. And remember, K0 d times the square root of n1 square minus n2 square is actually equal to V. And if we replace cosine theta with square root of 1 minus sine square, we end up with this. Now, the square root expression in here and the square root expression on the bottom can be combined together, and then we will add n2 square and then minus n2 square for the top expression, then essentially you can find that the first two terms is exactly the same as the bottom one. The last two terms combined with the bottom numerical aperture is going to be 1 over b, b. So this altogether we simplify the expression into v times square root of 1 minus b. Now the phase shift for the lower boundary, we can also do the similar analysis. What we need to do is to add the bottom expression here with n of 2 square and minus n of 2 square. So here we go. So if you do that and you divide the top and bottom by the numerical, by n1 square minus n2 square, then you will get this. And you can simplify this into this manner. So b divided by 1 minus b, and then take the whole expression is square root. So this is the phase shift. So for the phase shift hitting the upper boundary, the phase shift for the refraction on the upper boundary can be evaluated in this manner. And again, we are going to do the same plus n2 square minus n2 square for both top and bottom. And then here we go. What we can do is we start with this one here, and we divide the top and bottom by n1 square minus n2 square, and that's what we get. Square root of a plus b divided by 1 minus b. So altogether, we have a characteristic equation like this, and this is the universal BB dispersion characteristic. And this equation has been used in the optics field for many, many decades. And surprisingly, this equation can be used for TM modes as well. But before doing anything, you need to do some adjustment if you will deal with TM modes. So for TM modes, we know the B number. We also know A and B's are different. The V number can be the V number are not the same. And now we are going to take a look in equation 1x. We have this equation, and the phase shift caused by refraction on the dielectric interface can be obtained as this one for free. For the upper boundary and for the lower boundary. And if you just substitute these two equations into here, you won't get anywhere. The final equation is going to be more complicated. However, there is a way to further simplify, and you can reuse the same BB equation even for TM modes. All we need is to readjust B. So original V have no this factor, but for TM mode, you need to add this factor in. And this is so-called the reduction factor. And for B, you need to add this factor in. And for A, the asymmetry factor, you need to add this factor. So how can you calculate this Q of 1, 2, Q of 2, 1, Q of 2, 3, for example? We all based on this formula. And this formula This Q of ij is known as reduction factor. And you use this factor to calculate Q12, Q21, Q23. And then you just substitute back to convert to V value, P value, and A value. And then you will find all the parameters. The process is very simple. And if you want me to show you the source of this, the reference to this formula, yes, so here we go. This technique has been invented in 1987. Yeah. Okay. So before closing this episode, I'm going to show you the PV curve. So let's take a look here. I have got the Matlab equation. Let's remove this one first. So this Matlab equation, you can find these Matlab equations in the description section of this video. And if I run this software, I will end up with this PV curve. The vertical axis represents P, while the horizontal axis is the V number. So how about these different colors curve? Yeah, this is for different value of A. For example, the blue one here is for A equal to 0, and the red one here is for A equal to 1, and the yellow one here represents A equal to 10, and the bottom one, the last one, A equal to 100. And we got all this mole characteristic for all mole number. This is from family of curve for mole 0, and this one is mole equal to 1, m equal to 1. This one, m equal to 3, m equal to 4, m equal to 5, and m equal to 6. So now, when you need to solve the problem, all you need to do is to draw the vertical line representing the value of V. The V can be calculated using the formula that I have given in the slide. It can be V equals to, it can be V for TE mode, or alternately, you can use V equals to, V specific to TM modes. Now, for example, I have calculated the value of B, and the value of B is 6.37, for example. So all I need is to put this into the graph, and I'm going to show you. So I put it. So what you need to do now is to identify the total number of modes for this waveguide. You need to check whether there's any crossing for this vertical line. So according to the graph here, you have got only two groups of lines, one for m equal to 0, the other for m equal to 1. So you can rest assured your waveguide can support basically two modes for TE mode, and I can tell you for TM modes as well. And now let's take a look in the crossing here. The upper one here is for A equal to 0. So you need to know the asymmetry factor. Different asymmetry factor will end you up with different value of P, and as a result, the crossing point will be different. You need to choose the right one for a specific A number. And from there, you can work backward and you can find out the propagation constant. Okay, so if you have further questions, please let me know. You just enter your question in the comment section of the video. Thank you. Bye bye.